Okay, this is a supplement to the previous video concerning Rosemary Ainslie's claims about the Figure 3 scope shot. Some people have told me that my scope traces didn't look sufficiently like hers, and I tried to explain that that was because I was using lower battery voltage and less lead inductance in the batteries. And so what I've decided to do is to repeat the demonstration very quickly, just to show that that is in fact the case. So here I've got, before I had two batteries, now I've gone ahead and cleared off some space on my rather crowded workbench here, and now I have three batteries in series, three 12-volt batteries with a little bit more lead inductance in the jumper cables. I've also put an inline fuse in there just for safety purposes, and it's not connected right now. This is the inline ammeter on the negative side, just a DC ammeter. This is my venerable Fluke 83 multimeter with the Exitech temperature adapter and a thermocouple. The thermocouple is attached to the Q1 MOSFET heatsink. So here we're monitoring the temperature of the Q1 MOSFET in degrees centigrade. Okay, and then over here we have the load in an oil bath, and now stuff is starting to fall over. Okay, so I'm monitoring the temperature of the load with this analog thermometer, and right now it's heated a little bit from my previous rehearsal. It's showing about 85 degrees Fahrenheit right now, 84 to 85 degrees Fahrenheit. Alright, now that's the temperature of the oil. There's 250 milliliters of USP mineral oil in there, which, if I recall correctly, has a specific heat of 0.84. So it's easy to calculate from the temperature rise how much energy you've put in. And it's in an insulated container with a known leak rate of power, so I know how much energy I'm putting in based on the measurements. Okay, and then here's the tar baby itself. Everything to the right, or to the left here rather, these boards are not being used. They're actually not even connected to the circuit. They are the independent 555 timer and charge pump inverter that allow the thing to be run independently without a function generator or external battery besides the run batteries. And I have the oscilloscope probe hooked across the 0.3 ohm current viewing resistor, and the function generator hookup is now, as Ainslie has showed on her board photograph, not in the correct position which is shown on the schematic diagram. The function generator black lead is now connected to the negative rail with all the other negative probe connections and all the rest of that. And that's wrong, of course. It needs to be on the other side of the current viewing resistor, because this connection bypasses a current path through the system, and I'll illustrate that for you. You may recall that the very first thing I did in the previous demonstration was to show how the function generator's current showed up on the current viewing resistor's trace. And we'll do the same thing again. Bottom trace here is the function generator's output, and it's my scope is still warming up, so let me correct the baseline position. There's the baseline for that, and there's the baseline for that. Both channels DC coupled. So this is the function generator output at 5 volts per division, and this is the current viewing resistor's output at 2 volts per division. We're looking at that through a 10x attenuated probe, but it's displayed at 2 volts per division. Okay. 0.2 there times 10 is 2 volts per division on the B trace. Alright. So the B trace is monitoring the current viewing resistor. The A trace is monitoring the direct output from the function generator through a BNC connection directly to the function generator itself, and we're triggering off of the sync output of the function generator to the external trigger input of the HP180A oscilloscope. Alright, so now let me show you what I mean. So before, when I turned up the function generator amplitude like this, what you saw was this really nasty, huge current signal in the current viewing resistor, but now you don't see it. Why? Because the ground lead of the function generator is now at the common circuit ground position, and that current from the function generator is now bypassing the current viewing resistor. Okay, because of the location of the lead. All right, so now I'm going to turn that back down. That's without any power. Okay, remember this, 25 degrees C on the MOSFET, and now I'm going to go ahead and hook up the power. Alright, so this is the DC current through the system. Alright, it's just in line with the negative battery feed there. Okay, looks like we're all ready to go. Alright, so now what I'm going to do is turn up the amplitude on the function generator until we get some switching happening. There's our oscillations coming in, and I can tell from here that we've actually already turned on the Q1 transistor in that little hump there. Okay, but if I start playing with the function generator offset, I can achieve a setting where we have a trace that looks almost exactly like, in fact, exactly like Ainslie's current on trace. This is the input to the gate. Nice fuzz on the bottom, just like she shows. The blue trace on her scope shots. This is the golden trace. That little peak right up there indicates substantial current flowing through the Q1 MOSFET. Remember that the RF screws up the reading on the thermometer. So what I'm going to do is turn that down, and then we'll take a reading on the thermometer. Okay, so you can see that that current did warm up this MOSFET, right? And it did warm up the load. We're at 89 degrees Fahrenheit now, okay? Alright, so let's get back to that setting. Play with it a little bit more maybe. Alright. So remember, we're looking at the gate signal at 5 volts per division, so we have about almost 10 volts now, 7.5 to 10 volts. Let's pump it up a little bit more. Alright. And then we put the negative offset in so that we get a trace that looks just like what Ainslie's trace looks like when the current is flowing. This is the figure 5 trace, a little bump there. DC indicates that. RF screws up with our temperature, so I'm going to quickly turn the setting down to where we have no oscillations, I think. We're still getting Q2 oscillations, so there. So 34, so we're raising the temperature on the MOSFET. Back to Q2 oscillations. This thing oscillates the Q2s with almost zero amplitude from my function generator. Alright. Alright, so there's something very, very much like what we're seeing from Ainslie's scope shots, right? And fair amount of current. Load is heating. And notice where that current indication is right up there. Now I'm going to fail the Q1 MOSFET simply by unplugging it. Okay, I just unplugged it. Q1 MOSFET is unplugged. Does this look familiar to you at all? We're still pulling some DC current. Turn down that amplitude just a little bit there. Alright, so now as you can see, we have the gate drive signal. Good gate drive, 10 volts. or even more. Get a lot of gate drive if we want, because this is a powerful function generator. But if we leave the gate drive at about 10 volts, 10 or 12 volts, just like Ainslie has, and then we plug that Q1 MOSFET back in. Oh, I forgot to show that with this setting we don't have, we just have oscillations there. We have very little current flow in the system. Okay, so now I'm going to plug the Q1 MOSFET back in. If I can do it with one hand. Point there. Okay, so that's what it should look like when there's actually a functioning MOSFET in there. Current is flowing. Load is heating. And when that MOSFET fails, point, you get the Ainslie Figure 3 scope trace. Exactly. Thank you for watching.